and welcome back to Calculus 1. It's still Saturday. It's always Saturday because I teach this class only on Saturdays. 4.9 Antiderivatives. So, as you know from your previous experiences in mathematics, there are additive inverses, which means that if you add A to its opposite, you get 0. You also know that there are pairs of opposite operations, which is that if you have, let's say, x plus 3 equals to 5, you use the minus 3 to both sides because addition and subtraction, right? So they add to 0, and you are able to solve this equation and get x equals to 2. So we have additive inverses, numbers that are opposite of each other. We also have operations that are opposite of each other. And now we go one step further. Opposite operators, which will be the derivative and the integral, will be opposite operators. They undo each other. So in the same sense, where you have positive 3 and negative 3, right, or addition and subtraction, or multiplication, division, undo each other, you can do that with derivative and integral. So we call this one the antiderivative, also known as the integral, which is the preferred name as soon as we are done with this lesson. So what is its purpose? It's to undo the derivative. If you say that the derivative of x squared is equal to 2x, then that means that the integral of 2x dx, the antiderivative, must be x squared, because it's supposed to return the input of the derivative. However, there is an issue. There's always an issue, right? What happens if you have dx of x squared plus 100? What is the derivative? It's still 2x, right? And if I am to write the integral, I'm going to get x squared again. I don't know how to get this plus 100. And no matter what I write over here, x squared minus, I don't know, 7 is 2x. You see, derivative destroys this piece of information, and this piece of information cannot be retrieved. This constant, the plus 100, the minus 7, okay, the plus 0 on the first one. So what we do is we put this plus c on each one, because when you are faced with the integral without having the knowledge of what happened with the derivative prior to that, you can integrate, but you don't know how to retrieve this constant part. So every time you solve an integral, take the antiderivative, you will have to put this plus c. And that compensates for whatever constant might have been there, which was wiped out by the derivative procedure. I don't have much to teach in this particular section because of the fact that every single formula for derivative is going to be read backwards as the integral formula. There is one that looks different because we are kind of lazy, but other than that, everything else is going to be the same. So you have that the derivative of a constant is equal to 0. Integral of 0 dx is 0 plus c. So c. This is the one that it's a little bit different. Derivative of x to the n, or any power, can be fraction, decimal, whatever, is n x to the n minus 1. That's the derivative. You know this from chapter 3. Now, over here, we are not going to actually take the derivative of nx n minus 1. We're just going to say x to the n and write it as x to the n plus 1 over n plus 1 plus c. So that's the one that it's a little bit, that looks different, just because it's the next term. And you'll see it actually works. Then you have the derivative of, let's say, ln x. You can put all of these there. Is 1 over x, which means that the integral of 1 over x dx is ln absolute value of x plus c. You have to put that absolute value there. The derivative of e to the x, yes. Is e to the x. What's the integral of e to the x? Yeah, I know, this one is very tough. Because it has plus c, which takes off points if you don't have it. What's the derivative of sine x? So what's the integral of cosine x? You have to be this read backwards. And what is the derivative of cosine x? So what's the integral of sine x dx? Negative cosine x plus c. You guys know the entire list, because what you need to do is to look into the derivative chart and read it backwards. That's all it is. With the exception of, oops, spazzed, of this one, the polynomial one. That's the one that you are memorizing now. The exponent goes up by 1 divided by the same exponent. And I'm just going to put 3 dots over here because this is going to go on with all of your other trig stuff and whatever else you come up with. We do some examples now. How much is the integral of square root of x dx? Yes. So I will rewrite this as x to a 1/2. And then I will use the formula x to the n plus 1 over n plus 1. So x to the 3/2 divided by 3/2 plus c. This plus c is not there for decoration. We need it. We really need it. So what's the actual answer? It's 2/3 x to the 3/2 plus c. How much is the integral of secant squared x dx? Tangent x plus c. Good. Why? Because we know derivative of tangent is secant squared. I hope. Happy? Let's take a look at some rules so we can have more interesting problems. Rules, properties, whatever. Say, well, first one, let's try those rules. Integral of the constant times f of x dx is equal to, you kick the constant outside, and then you can just integrate. Integral of the sum of two functions is actually integral of each one of those functions integrated separately. And if it's a subtraction, well, same rule. All right, now you have to be very careful with division and multiplication. They do not work like this. We have rules for those. Remember how for derivatives you had a product rule and you had a chain rule and stuff? You are going to have for integrals use substitution, integration by parts, partial fraction decomposition, trigonometric substitution, the whole palette of interesting tools, most of them taught in Calculus 2. So we are only going to learn one of those, which is U sub, and that U sub is going to be chain rule backwards. That's it. When you reach chapter 7 in Calc 2, which is next semester, we do integration by parts, partial fraction decomposition, trig integral, trig sub, and all of the other cool stuff that it's there. So these are the rules and properties. And now I can ask you how much is the integral of 5x cubed plus 3 sine x minus e to the x, everything dx. Well, you can break this into 3 integrals, kick all of the constants in front of the integrals, and then just solve each one separately. So I technically ask you 3 problems in this one line. Because your job is to split into 3 integrals, because you can. Keep every constant outside of the integral, because you can. Integrate basic functions according to your rules, and then be done. Now, can this be done immediately without doing any of those steps? The answer is yes. That is the goal. You will learn how to just look at this and write a solution rather than writing every single one separately and so on. You are writing these things separately only today. So now you're supposed to write 3 integrals, one step, then keep the constant in the next step, and then write a solution in the last step and you're done. Five over 4. It's 3. Yes, 5x cubed. I'm waiting on you. Nothing. He's absolutely nothing.
Well, that's what our whole row is doing. That's what he needs.
It's playing with you. One for all. Maybe I'll find mine. Okay. So after sufficient struggle, let's take a look. Again, all of this work you are going to cut out quickly, but let's write it for now. So I'm going to apply integral to each individual term. And then I'm going to kick these constants outside. Observe that each integral has its own dx. Integral dx is the notation. You have to use dx on every term. And you will see in the next lecture why. So now, when you have this, the integral is x to the 4 over 4 because it goes plus 1, right? And then we have plus 3. Integral of sine is negative cosine x. And then minus the integral of e to the x is into the x. And we have a plus c. We don't need plus c for every single term. We just have overall plus c for all of them. You could have had C1, C2, C3, but then they all combine into a major C. So there is no reason to have multiple C's. Now we just simplify this. So 5/4 x to the 4 minus 3 cosine x minus e to the x plus c. And that's the answer. That's it. We really don't have much in this section other than getting used to the integral notation, getting used to the idea that you have these going backwards and so on. So let's see. So here is another example that you can consider. Problem 31, it says 3x minus 1, no, 3x plus 1, and then 4 minus x dx. Do we have a rule for multiplication? We don't, right? So what is that you have to do? You have to FOIL. Must FOIL. Must FOIL and then go on. So we FOIL. We have 12x minus 3x squared plus 4 and minus x. Everything in parentheses dx. I will explain why you have to have these parentheses as well. If you have multiple terms, you need parentheses. So now I am going to put everything on the pile in the decreasing order exponents. So we have negative 3x squared plus 11x plus 4 dx. That's 12 minus x is 11x. 12x minus. And now we integrate each one individually. So I will still write it one more time. Negative 3x squared dx plus integral 11x dx, and then plus integral of 4 dx. So what do? Kick the constants outside. Again, this you will be skipping all of this work, writing all of this work. I mean, you will have to integrate. And what we get is negative 3 x cubed over 3, because it is x to the n plus 1 over n plus 1. N is 2, so 2 plus 1 is 3 over 3. Plus 11 x squared over 2, right? Exponent was 1. And then plus 4x. Integral dx. Well, there is 1. There is a number 1 here that has the exponent of, which is actually x to the 0. And then when you add 1, you get x1 over 1, which is just 4x. Plus c. These cancel. So negative x cubed plus 11 over 2x squared plus 4x plus c. Here's a wonderful example for you to enjoy, relatively speaking. Okay, have fun. We'll see who's. Let's take a look at this problem together. I'm going to skip one of the steps now. And actually, wow, I just said some word in Serbian. Actually, what I'm going to do is I'm going to do two steps in one step. So I'm going to kick the constant outside and rewrite this as x to the negative 1/2 dx. That's the first integral. Plus kick the constant outside, write it as x as a positive half dx integral. So that's what I do. And then I solve. So I add 1. So I have 3 x to the negative 1/2 plus 1 is positive 1/2 divided by 1/2. So that's the first integral. Plus 3. And now I have the second integral, which is x to the 3/2 when I add 1 divided by 3/2. And then I have a plus c. So now 2 in denominator goes and multiplies 3, so I get 6. And this is a square root of x. Plus the same thing happens on the second one, which is, well, actually 3 and 3 cancels. So I get 2. And then I have a square root of x cubed. And then plus c. I'm just going to make a note on the side, something from algebra that you guys should remember. And that is x to the m over n is nth root of x to the m. If you forgot this rule from algebra, so whatever was in denominator goes as the order of the root, and whatever is in the numerator, the upper part, is the exponent of the number or variable. So that's exactly what happened here. 3 stays as the exponent and over 2 becomes a root. Because you are going to see these as a 5th root and the 7th root, because it's quick and easy to make those problems. Awesome. And one more. Let's see something else from the you're gonna hate this one. I actually don't want to let you do this one because you might start doing it and then remember it wrong. So I'm going to actually work this one out. I'll give you a similar one to try and figure out. So integral of dx divided by 1 plus, let's say 4x squared. Chances are very low that you memorized this derivative. Inverse tangent. Nice. Nice. Inverse tangent. Yep. Mm-hmm. Yes.
Just inverse tangent.
No, there's stuff, but so actually, now that you know, I'm gonna let you figure this one out, and then we'll get one that is spicier. They have a whole section, I think 10 problems, asking you all the inverse ones that the formulas that you probably didn't memorize. So you can look in the textbook, look up the formula for integral for the inverse tangent, or yeah, it doesn't work. But it's getting there, close to. Well, actually, the first step is to write 2x everything.
I'm not gonna put one with a double angle.
No, unless you request.
No, I
Okay, I'll make it all right. Go away.
Yeah,
Go away.
it does.
You read the rules for the inverse. Good. So, work this one, but work it backwards. You have this side see how that affects. Yeah, but like, what if you like really hit it? What happens if I really hit it? I mean, you give it a shot. It's not efficient.
There's not
I'm not
anything in
sure
there, is
if
there?
that's possible. So, and I also don't have a pizza because it's a lab.
Where does one acquire such a thing? Wow. You said.
Well, I mean, like, if I'm gonna sit there, like, accidentally with my hand and be like, okay, it's not gonna pull over, but I'm sitting there, like,
Punching
thinking on it.
punching it.
Of course it's gonna break. So, like, you only get, like, a vertical lift up.
Yeah, some people actually need to put that on everything they own.
Yeah. Especially phones,
And the-
laptops.
Yeah, and their feet too. They can just go like. They won't fall.
Horizontal mission impossible.
I don't find it big if but I can't choose to stay where they go. It's like such a tough everything.
I'm not a big person.
I'm just having an image of the Spider-Man with the suction cup. That was bad. Yeah.
Hey, yeah, we're right here.
Ready?
You're gonna solve in like 2 steps.
One.
Wow. Thanks.
Let's take the derivative and check. And if it's not good, we fix it. So I have 1/2 tangent inverse of 2x. We copy 1/2, and then it's 1 over 1 plus 4x squared, and then the chain rule, because this was not x, it was 2x, the chain rule gives me 2, which will cancel the half, and I got the thing. This is why integration is so beautiful. Every time you integrate, it will take the derivative to check it. It's very quick. I'm sorry? No, I never. Where? The plus c is clearly there. If you here, it's too much of a zoom. As a plus c, this is over here is a plus c right there. I'll make a rainbow underneath that. Yeah. Colorless rainbow. This is how I feel right now. Yeah, it's on the exam. It's either plus c or minus 1. You can pick whichever one you like better. If you catch my drift. Plus c or minus 1. Yes. You see that we need it, right? You see that we need it? In order, when I took the derivative, it worked out. And now a tricky question. Let's see. Well, tricky question. I don't know. T plus 1 over t dt. We can use any variables. What would be the step over here? What do you think?
D upon D plus 1 by 2, or D by 2 plus 1.
Yes, we split this because it's a common denominator. So it becomes integral dt, because t divided by t is 1, plus integral 1 over t dt. So the answer is t plus ln absolute 1, ln of t plus c. Right here.
Can we just make like,
Clear, right? Good. What happened?
can we just do like D raised to minus 1,
I'm sorry?
D raised to minus 1.
No, because you will get divided by 0. Minus 1
So that would be
plus
D,
1 would be 0.
so that's
See, that's the exception. You know, here's that word with the silent K we mentioned at some point. You know that the derivative of ln x is 1 over x. If you are to take the integral of 1 over x dx and write it as x to the minus 1 dx and try to use the formula, which would be minus 1 plus 1 over minus 1 plus 1, you will get x to the 0 divided by 0. Right? You see, it doesn't work. You have to memorize, right? So let me just strike the red line and say nope.
one more thing.
Yes.
But if there is no ln x in the, I mean, in the differentiation, and it will just go up in the integration, then we can use it, right?
Nope.
I mean, will you, yeah,
We cannot use the formula for this particular situation. It has to be this one. Has to be this one. It has to be absolute value as well. There is no, so any other exponent other than negative 1, you are going to use the formula x n plus 1 over n plus 1. Yeah. It's just backwards from what you have up there for ln x. You prove the derivative and you just write it backwards. There is no excessive proof for it. I mean, I can also explain the reason for the absolute value if you are interested, because if you don't put absolute value, your answer is wrong. So that's another part to it.
yeah, well,
Because of the domain issues. If you take a look at the input function, right? The input function has the domain on both sides because it looks like this. ln x has only one side domain. But when you put the absolute value, it gives us the other side as well. So now you have everything but 0 in the input and everything but 0 in the output as well. So you must have the absolute values. Without absolute values, you only have half of the domain. Yeah. So that's why you must have absolute value. There is a reason for everything we do. All right. The last part of this lecture is calculating C. All right, so you really have to pay attention on this one because from this point on, you see it once, it's going to be back in Calc 2, Calc 3, differential equations, especially differential equations. So I'm teaching it now and you will know it after that for whatever class you take. So I have, let's say, integral of 2x cubed, no, 2x squared, let's say, 2x squared dx, and I want to force it to go through the point, let's say, 112. That's a point right there. And we call this one initial condition. You can call it initial condition. So now what do I do with this? Well, I integrate. So we know we're going to have 2x cubed over 3 plus c, which is 2/3 x cubed plus c. So this is your function, which is the answer. All right. Now, what actually should be denoted as a capital F. So now, use the point. The point says that the answer is 12 when x is 1. And as you can see, you can compute c from there easily. So 12 equals 2/3 plus c. C is equal to 12 minus 2/3, which is 11 1/3. So you will write that the integral, the function, is 2/3 x cubed plus 11 1/3. Or if you had a 34 over 3, whatever. How about I write it 34 over 3? Let's take a look at the book. Give me a problem 68 through 76. I mean, give yourself a problem. 68 through 76. Quickly. 72. Wow. How'd you pick the... All right, fine. Do you have a book in front of you? So you're supposed to figure out how much is P of X with computed C values. So what do? You integrate, okay? And then you compute the C using the point that is provided. And the point is provided, T input is 0, and P would be 100. Let's see what you get. So we are integrating because to go back from the derivative into our original p function, we have to integrate both sides. So the left-hand side will just give me p of t, right? Loses the derivative part. And on the right-hand side, I have to integrate 10 e to the negative t dt. So copy the constant. What's the derivative of e to the negative t? Yes. So it's going to be e to the negative t with a negative. Kick that negative out. And then we have plus c. So we found that p of t is negative 10 e to the negative t plus c. We have a point that says that when t is 0, p will be 100. So we plug that in. 100 is equal to minus 10 times e to the negative 0, which is just 0, plus c. So 100 is equal to negative 10 because e to the 0 is 1, plus c equals 110. So what's the function p of t? It's called the particular function because it's the function because of the point. The answer is negative 10e minus t plus 110. So we can use the initial point if we have it. And you know, usually in application, that's the one that you measure. Is anyone going to attempt using Newton's law of cooling to make the turkey? For heating or cooling stuff. So you can actually compute exactly to a second of how much oven should be on for a particular temperature of the turkey that you want. Unless you buy one of those lame things in a bag already that says cook for 63 minutes and then take it out and then throw it away. It doesn't taste good.
Use calculus to find out this 63 minutes.
I hope. All right. That's the lecture on antiderivatives. If you know your derivatives, you should be able to reverse them. The only new formula is the one with the polynomial where you get xn plus 1 divided by n plus 1. That's the only one. The rest is all the same, just working backwards. And yeah. Remember to split the integrals, to pick the constants out, to do all of these things, one step at a time in the beginning, and then later you will be skipping all of this stuff. So you will just be writing the solution. And the most importantly, at the end, know how to compute plus c. So if you have a problem and you have a point, then you can actually compute the values. That's called the particular solution, and this one over here was called the general solution, right? Because if you have the plus c, the general solution could be any of those curves. They're all stacked infinitely up, right? And then you have the one particular because they're out of all infinity that you get over here. This is the exact one that goes to that point because the point was used to determine it. All right, so we'll do 5-1 after short break.